Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's Design News webinar, Motion Control Solutions to Solve Your Engineering Demands and Challenges, sponsored by Maxon and PMD, and broadcast by Informa. I'm Chris Keach, and I'll be your moderator today. We have just a few brief announcements before we begin. First, this webinar is designed to be interactive. The dock of widgets at the bottom of your screen will allow you to learn about today's speakers, download resources, share this webinar via social media outlets, and participate in our Q&A session that takes place at the end of our presentation. Please note that during our Q&A session, we'll try to get to as many of your questions as possible. However, if we're unable to get to your individual question today, someone will get back to you after the program is over. And the slides will advance automatically throughout the event. You may also download a copy of the slides via the resources widget. Towards the end of the webinar, we will ask you to complete our survey found on the right-hand side of your screen. Please take a moment to fill this out before leaving us today, as your feedback will provide us with valuable information on how we can improve future events. And lastly, if you're experiencing any technical problems, please click on the Help widget found at the bottom of your screen, or type your issue into the Q&A text area, and we will be glad to offer one-on-one assistance. And now, on to the presentation. Motion Control Solutions to Solve Your Engineering Demands and Challenges. Discussing today's topic are Kristen Luwatsky, contributing editor at Design News, and joining her is Prab Gauri-Sankaran, VP of Engineering and Strategy at PMD. To learn more about our speakers, please visit the BIOS widget. It's now with great pleasure I turn this special session over to Kristen to begin. Kristen, take it away.
Thanks, Chris. Thanks to our sponsors, and thanks to everybody out there in Radio Land. We have a lot of ground to cover, so I'm just going to dive right in. I'm going to be reviewing the challenges, kind of focusing on some of the core motion control technologies that can address engineering issues, and then go through some use cases showing you how they can be applied to solve some of your headaches. First, though, let's start out with kind of a look at the overall hierarchy of needs. You've got end users, whether that's at the consumer level or industrial or manufacturing, basically. Everybody wants their stuff to work. If they are manufacturing, they want to be building quality products. They want high throughput. Everybody wants it to be inexpensive. The OEMs developing systems, they want easy design. They want ease of integration. They want things to run. And if they need to troubleshoot or service it, they want that to be easy, and that holds also for the end users. Nobody wants to, have their equipment down. They need it to do the stuff it's supposed to do. But we've got a whole raft of other challenges that are layered on top of these basics. I mean, consumers want everything customized. They've been trained by, the cell phone industry. You can choose the color of the home button. So they want that, they want more functionality, and they want it right away. And that means that other businesses down the food chain need to be able to adapt. That doesn't just mean faster design and engineering cycles. It also means faster changeovers when you're manufacturing. Again, cost is always scrutinized, but you've got regulatory environments. If you're making medical devices, you've got to meet a whole bunch of marks if you're military and aerospace. And then we've got data stuff layered on top of that, data privacy. And a big hit is the skills gap going on right now. I mean, we lost a lot of engineering support during the Great Recession, but, your boomers are retiring, and that means that your machine whisperers who used to be able to put a hand on the machine and say, oh, yeah, why don't you just turn the pot over there and we'll get this up and running just right. They're gone. So we've got to figure out ways to work around that. But we've also got a pandemic in place. We've got social distancing. We've got fewer people on the floor trying to get stuff done. So there are a whole lot of headaches out there on the engineering side. But the good news is we've got some ways of addressing them. And it starts out with intelligence. I was talking earlier about how smartphones sort of increased headaches because people expect customization, but you can also think the embedded design world for making life a whole lot easier and more interesting for motion control, because now we've got a real focus on smart components. They've got, not just your PLCs and controllers, but things like drives and encoders and HMIs. You've got onboard processing power, you've got memory that lets you have a whole lot of built-in functions. You can have built-in oscilloscopes, you can have built-in filters, reconfigurable sensors. You've got components, a lot of them can act as data loggers, and everything's connected these days. Well, not everything. You can still get dumb components, but connectivity is pretty straightforward, and that kind of propels a lot of the capabilities we'll be talking about. So the intelligence, among other things, has enabled components to do a whole lot more. I mean, the classic model is, your PLC runs your machine logic, the motion controller does your motion control, it tells the drives how to commutate the motors, your feedback devices tell you how well you're doing to help you close the loops. Well, these days you've got drives that have motion control capabilities, you've got motion controllers that can do machine logic, you've got PLCs that can do a few axes of motion control, you've got HMIs that can be data historians, you've got integrated motor drives that can do it all. So these functionalities can really start solving a lot of problems for us. So let's look at one. Cabling, single biggest point of failure, it's those maddening intermittent faults because you've got wiring snaking all over the place. And if you're doing motion control, it's flexing, and you're going to get potentially fractures. Plus, it's expensive, it's heavy, it's complex, it's got a bigger footprint. So there is one good solution that drives can contribute that potentially it's not applicable for all applications, but in many distributed control architectures can actually be really helpful. Now, our classic design is centralized control. That means we've got a cabinet somewhere, and it's got a controller, and it's got the drives nestled in there, and everybody's wired together and pumping out heat. Now, the cabinet protects them from contamination, shock and vibe. Those herky motion controllers can handle really highly coordinated motion. But again, we got all that wiring, we've got to find a place for the cabinet, that one more thing to buy, one more thing to connect. It consumes energy because you've got to cool it. You've got more points of failure. So for some applications, it's absolutely the right way to go. But for other applications, we can look at potentially distributed control with these smart drives that have the ability to act as controllers, because they can be put together in daisy chain controller architectures, master-slave, where one drive is master to many slaves, or, each one is a master of the next. You're hanging your drives out on the motor, so you have much less cabling. You can apply things like regenerative braking with some of these smart drives. You've got the PLC handling most of your machine logic, but the drive is actually able to take care of much of the motion. And again, we get our savings with cabling. So what does that do for us? Easier integration. We've got lower failures, shorter runs, less flexing. It's faster and easier to replace. You've got lower weight. The weight can be substantial. If you're looking at a standard drive, you've got 4 wires involved there. Depending on your system and your constraints, that can be a problem. You also get a smaller bill of materials. Might be lower cost. No, it might not. These smart motor drives do cost more than dumb drives. That really is a project-by-project situation, but it's worth considering. Downside is drives are out on the machine. That means they're exposed to thermal swings, shock and vibration, being run into, but right application, they can actually be a really good fix. Another thing, again, we were talking about hey, you've got to speed up your design and commissioning cycles. So drives and, indeed all motion components are really getting more and more user-friendly. There's a drive toward using that, trying to consolidate power and programming down to a single cable. There's motion-friendly programming with pre-written code blocks. And that actually extends even in the control space. There's PLC Open, which has whole libraries of motion code blocks in multiple languages, in structured text and ladder logic and function block. So it's all there to use. Some manufacturers have pre-written templates for HMIs that are out there. Definitely talk to your vendor, take a look at your owner's manual. You might find there's a lot of stuff out there that can make things happen faster. And certainly with the connectivity, if you're able to get access through web servers, then you don't necessarily need to have feet on the floor in front of the equipment, which can be good. And then there are two particular functions that we can get from the smart drives: auto-tuning and sort of a sister function, vibration compensation, that really can bring big benefits. So auto-tuning, faster commissioning. I mean, the old way with PID loop tuning, that can take, it depends on the skill of the person doing it and the experience. You're looking at an hour, maybe more. I've heard horror stories about some axes taking a day. And, if you've got a small system, it's not a big deal. If you're doing 100 axis paper line, then yeah, that's going to eat up a huge amount of time. So auto-tuning drives have made a big jump forward now. Gen 1, they get you to a first approximation. You still had to get in there and start turning pots. But Gen 2 and Gen 3, they can really get you about 95% of where you want to be. And for a lot of applications, that's good enough. And if it's not, you can always get in there and work manually, but you're close to where you want to be right off the bat. And they're also able to really do adaptive tuning. Now, I was talking earlier about built-in functions. Part of that is built-in tunable filters. And in the case of drives, for example, you can have anti-slosh routines, which is always kind of a treat to watch. We call it up on YouTube or something. They'll exercise the drive, and it'll be ping-ponging all over the place. The drive takes that information and adjusts the filtering. You exercise the drive again, and the motion is really smooth and not problematic. So you've got that capability now. That doesn't just help with things like slosh and all that, but say you've got a problem on your equipment. So you've got a screw or a nut, you lose a preload, suddenly you're changing the vibrational frequency of your axis, and that's going to start affecting your product and so on. If your drive is able to detect that, it can adjust some filters to avoid exciting those resonances. Then you're going to be back to the performance you expect. Now, there's some perils there, because you don't want to miss the fact that you've got a physical problem with the equipment. You want your drive to send you an alert. But the thing that it does get for you is, while you are having your maintenance come out and take care of things, you're still putting out good products. You're not putting out crap. One second here. Now, the other thing is with the frequent changeovers I was talking about earlier, when you're, trying to churn out new products and things, again, adaptive drives can really be a big help on that, because, you've got your single frequency that's kind of your natural resonance of the machine, but layered on top of that, you've got your varying frequencies, and that's going to be, driven by the load and the axis. If you're changing your load, going from 8-ounce bottles of water to 12-ounce bottles of water or something like that, that's going to change the vibration and resonance. And that doesn't matter if you're bottling the same bottle for a year and a half till you fill up your factory, but if you're trying to change constantly, your drives can come in there and take over some of the work so that your engineers don't have to. Again, that's the drive's innate ability and also the software configurability, which is kind of the key thing that's going on right now, right? Because we've got software-defined everything pretty much. We've got software-defined networking and software-defined computing, and now we're doing software-defined motion. When you've got a lot of these functions built into the software or the firmware, then you have much more freedom, and you don't necessarily need to be physically there, which goes back to our skills gap issue that we've got coming up. Let's see, the other thing that you can do is you can use drive feedback for quality control. Now, this actually came out of NASCAR with the pit stops, right? They've got the hydraulic, pneumatic drills to put on lug nuts, but you know what? You don't get it done just right, and your driver gets out on the track at 195 miles an hour, and then they find out the wheel's not balanced. Not really a good look. So they started using torque profiles to be able to determine whether things were getting properly installed. So you can use drive to do the same exact thing in the automation world. If you're running a machine tool, you set up your ideal profile, you calculate the velocity and acceleration you need, and then you analyze what's going on during processing, and you can figure out whether the tool is behaving as expected and as required to develop quality parts. So that tells you ahead of time. It's going to save you on inspection, and it's also going to help flag whether you've got problems that you need to worry about. And that actually brings me to the next pitfall you can solve, which is that unscheduled downtime. You used to have reliability techs that would, sneaker net all over the factory taking readings and stuff. We don't have so many people in the factory. We don't have those skills necessarily. Social distancing means fewer people prowling around listening for noises. So your drives, they can monitor the motor, they can monitor themselves. You've got encoders capable of monitoring themselves. You've got all the IoT sensors for vibration and temperature and so on. So you can fold this all together. You can grab the data. You can process it in an edge device if you want to, or you can do partial processing, send it up to the cloud. That way you don't need to have that skill in your company. You can have an off-site third-party technician reviewing stuff. So that holds for predictive maintenance, but really just remote maintenance in general and how it might look for a drive. So torque is a function of current, right? And if your drive is getting feedback that your motor shaft or your load is not going where it's being ordered, it's going to modify the torque to get the load to the proper place. But something caused that change. So, it could be a jam, it could be, a bearing cage defect developing, you could have lubrication issues. So the key thing is now there's a problem. So your drive can send an alert. As we talked about before, it's also got the ability to apply filters to try to improve the situation in the meantime. But, you've got the right people with the right information in their hands, because everything is connected. They are able to look at it, potentially over a web server. They can potentially dial back in, although, I know there are concerns about that in some quarters. But the point is that you don't have to have somebody standing in front of the machine at the right time, and you don't find out late. You can get advance warning well before anything goes critical. And there are multiple modalities that can help us view this. Vibration is a really powerful tool. Machine conditions can change the frequency response, and it's simple as belt. If a belt is loose, you're going to have a lower resonant frequency on that equipment. If you just replaced a belt or you've just done maintenance and you over-tightened it, that's going to adjust the frequency as well. So, and also you can be tracking what's going on with your friction, because as we all know, friction shows up. Things aren't supposed to be rubbing differently than they once were, and it typically indicates a problem that you might want to check out. But you can't check it out if you don't know. And by the time things start making noise, that can usually be too late. Now, the other thing all of this lets you do is go into the model-based regime. And this, again, it's technology that is available today. So, the motor gets feedback on errors. It's going to adjust for torque, but that is going to change the vibration it knows from the models. So now it can estimate how the vibration would change based on the model. It can perform separate or similar exercise for friction. All of that gets plugged into the model and combined with the total travel distance, and suddenly you've got a drive that can predict failure of itself or other components in the system based on this model. And again, the whole goal is to try to get a handle on unscheduled downtime so that things are least possible disruption and running when we want them to run. So yay, all of this sounds great, but that said, there has been really slow uptake on predictive maintenance. People are concerned about cost. People are concerned about hassle. I think the last survey I saw indicated there's only like a 2%, a few percent uptake prior to the pandemic. Now, that has changed substantially from the people I am talking to, from analysts on up to consultants, and vendors say that now they've got lines, metaphorically Zoom call lines, going out the door of people saying, okay, now I'm ready to do this. But the upside is, we've been talking about those smart components. A lot of this stuff is already built in. You may find out that you've already got these capabilities in your drives, in your HMIs, in your encoders even. You've got, a drive that's got a rotating data logger that can store in a rotating buffer and export what happened around a fault so that but you can also grab all of this data in advance so you can be analyzing it. So brownfield installations may not be as brown as they appear, and if you indeed already have those capabilities, then you can start trying out predictive maintenance or remote monitoring without disturbing your functioning system, which is kind of the gold standard. Another thing I want to talk about is functional safety. And this is something that really has huge upside, especially for things like productivity, just overall. Old safety used to be great. Let's put in physical barriers. Let's put in light curtains. And let's put in a wall of relays. So anybody violates a condition, bang, the relays go, and you cut power. Now it's changing so that instead of, hey, cut power as default, it's not a response, it's a process. And because it's a process, that leads to a lot of benefits like productivity, like greater uptime, like reduced scrap. So let's look at some of the details, and I can, again, talk for an hour on all of this. The structure, it can be centralized with dumb drives and safety PLCs, but also increasingly you get safety-enabled drives that have all of these functions built in, as we've been saying, software. So key thing that basically everybody knows, or most people know about, is save torque off. Yay, you can remove torque to the motor, but you leave the drive energized so you can restart quickly. There is a variant on that, which is safe operating stop. That doesn't even remove torque from the motor. It just holds the axis at 0 speed. Neither one of these things actually stops the axis. So the key thing is you're going to need to do a preparatory step, safe stop 1 for safe torque off, which is the actual braking part, or safe stop 2 for SOS, which is the braking stop there. And there's also the brake control for primarily vertical loads. But the really interesting stuff here in functional safety is the motion-based functions, and that's your safe limited speed, safe direction, safe limited increment, safely limited torque, safely limited position. And again, this is let's bring safety by how we let the machine move, not by just pulling the plug. Safely limited increment, if your equipment gets jammed, instead of the equipment shutting down, people having to go in there and pull things out, they can actually use the power of the machine to jog safely and get the jam released. So let's take a look at how that might work. Cleaning activities, this is rollers in a paper plant, and the old way is shut everything down, go in the enclosure, clean a little bit that you can reach, step out of the enclosure, turn it on, jog it, turn it off, go back in, rinse, repeat. Takes forever. The new way, if you do it with functional safety, you can use safe direction and safe speed. That lets you clean continuously and remain safe. And machine builders are designing cleaning modes that can do this kind of stuff automatically. So the equipment spends more time producing and less time just being maintained. There we go. So food and beverage case study, they were using the clean and jog thing. It took them 6 hours a day to clean the equipment. When they applied the safe speed, safe direction, safe position, cleaning cut down to 2 hours a day. So basically they saved a half shift of production, which is mind-boggling to think. And basically what they did is they did it all in software with a smart drive. Or actually, it could also have been done with a thumb drive and a safety PLC, but the capability is the key thing here. Now here's another example. This was manufacturing fuel injectors, and they were using functional safety, but the way they were using it was let's keep the equipment moving at safe limited speed around the operator, which was great, it helped. But the key thing there when they started looking at it is, when it's moving toward the operator, yeah, we definitely want to keep safe limited speed, but when it's pulling away, it's not going to hurt them. So they changed they reconfigured the system. So now the machine pulls away at top speed, and that led to a 10% reduction in cycle time. Now, you might sniff 10%, that's not wow, but looking at 10%, that means you can increase production without any capital expenditure, or you can maintain your levels, but fewer operators or fewer hours. You can use that time for maintenance. You've got options, and you're getting savings, and you're doing it with software. The other thing that it can do is bring out new opportunities, and here the best example is collaborative robots. People started doing this with the ability to control motion, because you can do safe limited speed, safe limited torque, safely limited position. So you can make sure that just the motion of the robot allows it to safely be around humans without, knocking it silly. Obviously, there are other things you have to do to collaborative robots to make them safe beyond those, but the functional safety is absolutely critical. These are not the only constraints, so let's go back to the hardware sphere and talk about space and size. applications are going mobile. You see it all over the place. We've got AGVs, we've got UAVs, unmanned aerial vehicles. You've got mobile robots. You've got telepresence robots in hospitals. But even if they're not moving, things still are space constrained. Robotics, they want them to be small. There's limited real estate. And I had integrator once tell me years ago, there are two things always in short supply on the factory floor, and one of them is space, and one of them is air or water for cooling. So motion control is doing something there to take care of it as well, and starts with the motors. People are using specialized windings, using flux focusing techniques to make the motors less copper-centric. That makes them smaller. And obviously the shift toward rare earth magnets made everything smaller and lighter. But people are even moving beyond that today, particularly since the rare earth bubble kind of pops after a while. Sensorless vector control in some motors is also an interesting technique, and this applies really to brushless DC motors. Now, usually, the standard design is monitor rotor position for commutation using a Hall effect sensor, but you can also do it with back EMF, and that gets rid of sensors, again, smaller, lighter weight. Now, it's not as with all things in engineering, it doesn't apply everywhere. If you're at low velocity or you stop, your motor's not going to generate any back EMF, so it's application dependent. But another technology that is very useful for size is your frameless motors. People use those especially in robotic joints. They get delivered, instead of being housed, they're delivered as separate rotor and stator. So they really support innovative designs of all sorts. Takes a little more knowledge and skill to use, and you want to be careful because those motors can pinch fingers, but definitely worth considering. The other thing, integrated motor drives. I mentioned that above, but if you have everything all in one package, it's easier to put together. You've got less cabling, you've got a smaller footprint. I mean, we're kind of seeing the overall variation on the theme, right? Drives, we've got the incredible shrinking drive thing going on, as you can see in the table. There's a real focus, especially for portable designs, on high power density drives. Once again, we're looking at the ICs for the embedded sphere that are making it possible to make much smaller and much more functional drives. You've got a whole choice of form factors. It's not just house drives anymore. You can get them at the chip level, the board level, the module level, depending on your in-house engineering capabilities and the demands of the application. And it's not just in the drive sphere. Controllers, same thing going on. You've got a lot of different packaging options, real emphasis on form factor and shrinkage. And at the same time, you've also got the availability of integrated sub-assemblies. One of the things I tend to harp on is that motion control is, very much an enabling technology. And in a lot of cases, OEMs, their secret sauce is something very different than figuring out how to move stuff from point A to point B. So the integrated sub-assemblies, if you're doing an HEV and you can just buy an integrated wheel drive, then plug it in and bolt it on, yay. So there are offerings like that around as well that are kind of making life easier. Another problem that we can solve with motion control is limited energy. Now, I started out to just call this battery operated, but it really is more than that, because with battery, yes, your portability is key. Your performance can change over the charge-discharge lifetime of your battery, and it's not going to help you very much to have a portable design if it's always in the charging bay. So, that's problematic. But the other thing is, even in a factory, power matters. I mean, for servos, energy is about 25% of the lifetime cost of ownership. So that winds up being an issue. It's the overall capital outlay for power. But the other thing you've got going on is a lot of your utility companies scale rates depending on the peak power usage. So the lower you can keep that, the better off you're going to be long term. And here too, yay, drives to the rescue. We've been dealing with a lot of high efficiency designs, but also let's come back to the whole regenerative drive thing. You probably know you decelerate a motor or reverse it, it becomes a generator. And that leaves you with a lot of power being pushed back through the system. Now, standard operating procedure is you dissipate it through a resistor, but what does that do? That generates a bunch of heat that you got to deal with, which is not necessarily the optimum. But you can also harvest that energy, recharge your battery, as any Prius owner knows. You can store it in a cap, or if you're connecting multiple drives over a shared DC bus, you can actually transfer that energy to your other drives. And then the final thing is, don't forget these drives are smart enough that they can be programmed to act on, power constraints. So, is the drive in an idle state, or is it, does the drive sense the system in an idle state? So maybe it's appropriate to turn off. Does the drive need to adjust because of factors in the loop? So drives can actually act as power management tools as well. So that's kind of the end of my thing. That really comes down to me always. There's no perfect solution. There are a lot of capabilities out there in motion control components, especially with the connectivity issues that can solve a lot of engineering headaches. And with that, I think I have come to the end of my high-speed talk, and I'm going to hand this right back over to you, Chris. Thanks, everybody, for listening.
All right, thank you, Kristen. And now Prab is going to go ahead and give his portion of the presentation. Prab, go ahead. Are you with us, Prab?
Yep.
You might
can
need
you
to
hear
come
me?
off mute. Yes, now we can hear you.
Yeah.
All right, go ahead, Prab.
Yeah. So, I was just saying, just piggybacking on Kristen's presentation, she touched upon a lot of the pain points that OEMs have in terms of distributed motion, built-in functions, and functional safety. So I just wanted to take a slightly different take here, just to identify where the OEMs come to us with in terms of problems. It always comes down to weight, power, and heat. They want to try and achieve something in the smallest space with the least amount of power and being thermally efficient. So we get inbounds from lots of different areas, from lab automation to medical devices to AGVs and mobile robots. And this is a common theme, regardless of where the end machine goes. They have all these pain points that they want to solve. So one of the trends that we are seeing, just as a practical tip, is there's a push to, obviously, the brushless BLDC motors were the king of motion. There's a trend with these closed-loop steppers where you have a lower-end, cheaper step motor. They add an encoder to it, and it acts like a two-phase BLDC setup. And this kind of gives them the capability to get to smaller form factor, but still be able to solve these other problems, right? Like get to less noise and no lost steps and still get the positional accuracy. So what we're trying to show in that waveform is, it's a traditional step motor has this problem where it just bounces around at the trough, trying to stabilize itself. Whereas a closed loop with an encoder kind of gets you the benefit of acting like a brushless and being operating at the most efficient point. And we're starting to see a trend towards more and more applications moving towards this closed loop stepper. In addition to these, obviously, things that Kristen didn't touch on, but traditional to motion control is the advanced control techniques, right? Like FOC and current control, just operating it at the most efficient point. So you could kind of achieve all these things that you're trying to get to. Just switching gears to, Kristen had talked a lot about intelligent drives that can do all. So this is one example. So if you see on the right, on the bottom, this is one of a newer drive that we've launched. And it's trying to hit all the pain points that Kristen had talked about. So it's a really small form factor, but it can still drive up to 1 kilowatt of power. But there's also the trend of this distributed architecture where you want a lot of different host interfaces and you want one of them to act like a master, and you can daisy chain and the rest act as a virtual axes. So you're talking to one and you're able to address 4 6-axis setup, and it simplifies your whole product development. And like Kristen talked about, there's a C-Motion SDK. It's almost like a function library that you can pull from. You have prototypes of end machines that you want to create, and it gives you a very, very good quick starting point. And you plug all these C blocks together, and you're able to get to your end application quicker. And the other thing we are seeing is a request for all sorts of host interfaces. So in some cases, it's CAN, serial, Ethernet, and the capability, as Kristen talked about with IIoT, Ethernet is becoming more popular because they want the higher bandwidth, where there is logging, the rotary buffer that Kristen talked about. There's a lot of logging that happens on the drive, but there's enough of a high-speed pipe to get that data out so you can do some sort of predictive maintenance. And with this drive, what we've tried to do is it has the capability to close all the loops, do all advanced motion control, but still has enough horsepower and bandwidth left. We call it a C-Motion engine where user can write code on the drive and can do custom stuff. It could be predictive maintenance stuff. It could be functional safety. It could be safe motion, where they can do the higher level functions in the embedded processor there and kind of adapt it to their end use case. And the other use we see, Kristen had started off the whole presentation saying there's a trend to mass customization, right? So this gets you to be able to customize it to your end application. You can write user code, download to it. You also get the capability to tune and reprogram the motion controller inside the drive, so that it's kind of trying to address everything that Kristen talked about. But as she said, it's not a single solution for all problems, but it provides all the building blocks that you need to create an efficient end product. So I'm a pretty visual person, so I tend to like to see how does this drive get used. One example, this is a rendering of a robotic arm. So this is where we talked about the distributed architecture. So each joint, each axis would have one of these drives locally mounted right at the axis. It minimizes cabling, lowers your weight, and it has to be small enough so that the robot can be implemented. Like she talked about the collaborative robots. This is one example of those. And where you're putting a drive for each axis, and it's distributed and spread out across all the axes. And we've seen OEMs kind of do this common motion module. They would build one module which controls one axis, and then they would replicate and use it to control lots of different axes. So they're able to expand and deploy and get to market a lot quicker. So with that, I'll kind of stop just to and hand it back to Chris for questions.
All right. Thank you, Prab, for a great presentation, and thank you, Kristen, also for a great presentation. Now, before we begin with today's Q&A, please direct your attention to our webinar survey, available on the right-hand side of the presentation window. If you close the survey, you can reopen the widget by clicking on the icon along the bottom of your screen. Thank you in advance for filling out the feedback form. Your participation in this survey allows us to better serve you. We're going to now move on to the question and answer portion of our event. As a reminder, if you'd like to participate in our Q&A session, simply type your question into the text box located to the right of the presentation window, or you can click on the Q&A icon at the bottom of your screen. And please note that we'll try to get to as many questions here as we can. However, if we're unable to get to your individual question today, again, someone will get back to you after the program is over. So let's take a look at some questions for you here, Prab and Kristen. Kristen, we have a question here for you. I think it says, I'm interested in some of these remote monitoring techniques, but we don't have the skill sets in-house. So what are my options?
Well, that's one of the advantages of being able to have the connectivity. You don't necessarily need to have, a level 3 of reliability tech able to look at all of this. It's a lot of services will monitor the data that gets sent up to the cloud so that they can, and the key thing is to also have some sort of a protocol for what happens when that data gets sent up. Your reliability tech looks at it, says there's a problem, then they know to reach out to maintenance or that sort of thing. So, you don't have to have all of those skill sets. And I know that there's concern in the industry about security and so on, but the key thing to remember with the whole remote monitoring predictive maintenance, it's pushing data off the factory floor or wherever. It's not allowing control to come in. So, that's something that does kind of address people's security concerns a little bit more.
All right, thank you, Kristen. Another question has come in and says, a lot of these techniques require connectivity, either within the floor or outside. So how do we handle cybersecurity?
A lot of this equipment is already pre-configured for security. If you've got edge devices, for example, the basic model is data comes off of the equipment, it goes to some kind of an edge device to get pre-processed and then packaged to send out to the cloud. So you can either do, number one, have your edge device do a lot of the processing and have either your in-house people who are off-site, or your third party access them through some sort of a web portal, or it can all get pushed out to the cloud and get accessed through a web portal in the cloud space. So there are, companies who specialize in building these portals and, following kind of your standard cybersecurity encryption practices and so on. And again, if we're talking about pushing data out, it's much less of a risk.
All right, thank you, Kristen. Another question has come in asking, what are the differences between centralized versus decentralized controllers, and why would you choose one over the other?
Yeah, I can jump in here. I think it's more like we talked about, Kristen showed a couple of slides, and I talked about on the robotic arm. It actually boils down to your end design of the machine, how separated they are, how big is the machine. For example, if you're looking at a DNA sequencing machine with lots of axes, it's a lot more work to make it centralized, and you're adding a lot more cabling and weight to your solution. Their distributed architecture makes a lot more sense, similar case with robotics. So it depends on your end machine design. But if you're making a really handheld kind of tool, it's all in a small space, so a centralized could work. So it's on a case-by-case basis. But what we're trying to show is just the distributed architecture, you don't lose much. Before, there used to be slower loop rates or slower response rates, but with advancements in all the microcontrollers and stuff and the control techniques, you're able to get the same performance, whether it's centralized or distributed.
All right, thank you, Prab. Another question has come in asking, do you use mainstream encoders for closed-loop stepper applications?
Yes, it's actually it's a traditional encoder. So you use a step motor with an encoder. So you're closing the loop, the position loop, with your encoder. And one thing I wanted to try and mention, and that was the encoder technology is also progressing. Like Kristen talked about with the regular semiconductor, there's also a lot of trends in terms of encoder technology. So you're starting to see sine cosine encoders with very high nanometer precision being available at reasonable prices, and the processing power, like on, for example, our intelligent drives can support sine cosine because off-the-shelf chips can support all the processing that's required to be able to get precise position out of it. So it's coupling a step motor that's a cheaper, lower cost approach with the traditional encoder gets you the best of both worlds and gets you a two-phase brushless implementation.
All right, well, thank you, Prab. That looks like all the questions that we do have for today. Once again, if we did not get to your individual questions, someone will be getting back to you after the program is over. I'd like to thank Kristen and Prab. Design News appreciates your time and your expertise on today's topic. I'd also like to thank our sponsors, which are Maxon and also PMD. And we'd also like to thank everyone in the audience. We appreciate your attention and your participation. Within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. Please feel free to invite your colleagues and peers who may not have been available to listen to today's event. This webinar is copyright 2021 by Informa. The presentation materials are owned by or copyright by Design News, Maxon, and PMD, and the individual speakers are solely responsible for their content and opinions. On behalf of our guests, Kristen Luwatsky and Prab Gauri-Sankaran, I'm Chris Keach. Once again, we'd like to thank you for joining us, and we hope you have a great day.